Our next speaker is Shijing from University of Washington.
Yeah, so before I go through my research talk, I thought I will do a little bit of the editor job here. So I'm associate editor for APL machine learning, and this is a journal. Like I have two scopes. We focus on machine learning for physical science and also the physical science for machine learning. So both like materials for machine learning as well as machine learning for materials. So the main thing I want to bring today is like we are having a special issue like on like machine learning for self-driving labs, and myself included, and also we have an amazing team of guest editors. So if you're interested in like submitting like your like work either on foundational models, on software, on data management, or like new machine learning approaches for like self-driving labs, feel free to like shoot me an email, and my email is here in my slides. Okay, so that's a little bit of the advertisement for our journal. So now let me start like to share a little bit about what I do as a researcher. So like today, like I decided to like condense like my several years of experience working at the interface of machine learning, material science, as well as high throughput implementation to like just what our lab did in the past 10 months. So like I thought it would be interesting for me to share a little bit of my reflection and also our approaches if you are one day you want to build a self-driving lab from scratch. To start with, I want to say like a shout to like a professor like Andrew Rosen, who also brought up a little bit of number counting of materials project. I had to check yesterday, and you can see it's like now like the highest number is around like 700K like entries. But I do want to bring a different highlights. I really want to everyone to think about the material project. We start to have the entry from 2011, and within these like kind of like 10 years, we have like this many of computational discovery and entries. Not only so, like I found like there's a paper about Alexandria like on database, and like it was a last year's paper. Amazing like a paper, but what really caught my eyes is like they were very humble by saying like the largest computational databases only contain over about 4 million materials. As experimentalist by training, when I did my PhD quite a few years ago back, I know just this May, like ICSD celebrated our 300,000 structures. This is a big milestone. So I think like in this room, a lot of you may be agreeing with me that our computational discovery is outpacing our laboratory realization. Not only so, this gap is widening every day. So then let's have the question, right, why we are here. So how can we close this gap? What is the lab of the future should look like? So I may say, well, we should be able to explore materials faster. They should be more accessible. If I have an idea today, theoretically, I think it would work, I should be able to access to a laboratory environment to quickly test it and give me feedback. Of course, all this like AI generated like knowledge, I really want to have the embodiment so my robot actually can execute what my AI algorithm says. So with this in mind, so in the next 15 minutes or so, I want to share like 3 approaches in the past few months our lab have been trying, which I kind of give them like a kind of a nickname in the way we try to develop a brain for the lab. We tried to design arms for our lab. We also try to build bodies. So let me start. The first thing is about like how can we implement a brain in like the labs. So here, the brain typically we refer to as the AI-driven parts for an automated platform. So you may be familiar with like when we want to transfer from manual to automated experimentation. So in this case, I'm being materials agnostic. So in general, like in the past, we may do synthesis by hands. Now we have like high throughput platforms, like they can do synthesis automatically. We used to take our samples to a different lab and measure it. Now, like we can have like a mobile robot to transfer our samples. And of course, similar for the characterization steps, it can also be automated. There are like several commercial options for the characterization techniques, such as XRD or like also XEM and so on and so forth. So where did I get this lovely automated laboratory photo? It's actually, I was very fortunate to be able to collaborate with our colleagues from PNL over the past few months. So here we have our collaborators, Dr. Yangang Liang and Heather Zhou, and they are the chemists like actually operating these like high throughput experimental setups at PNL. And the question is, even though you have all the automated steps, the question is after you've done this one loop, you synthesize the materials, you test them, what's next? You still need to make a decision. You need to have like some sort of intelligence saying, well, even though I have the high throughput capability, I don't want to waste my time and money and materials. So what we've been collaborating over the past few months is a graduate student from my lab and has been like joining this project. And her job has been like to develop a artificial brain for this system in the way like by way, I mean like our AI models take in the outcome from like the characterization. In this case, it is for redox active molecules, we take the HPLC variants. And then through building a surrogate model and then the decision-making steps, we give back the suggested conditions for the next round of synthesis. So like, as you see, like to start with, we are called like this is a multi-step synthesis into like mix the raw materials, stir them, heat them, and then like you take them for like characterization. And quickly, like we start to build this 4-dimensional space where we know the concentration, the volume, and temperature and reaction time all matters. With that information, so of course we went through like our like Bayesian optimization as our first approach. And because of its multi-steps, we also tried, in this case, 3 different sampling strategies, all based on Bayesian optimization to compare how we can sample the next experiment. Now, surprisingly, Bayesian optimization iteratively identifies the synthetic conditions with the highest yields for our like functionalization experiment to find the best annotated molecules for like a flow battery application in this case. So you can see like we had 4-dimensional space. Here I just chose like 2 of the dimensions as a demonstration. You can see from iteration 1 to iteration 2, like the posterior mean in terms of like the best expected outcome and the uncertainties are the output from the Bayesian optimization. And with 3 different sampling schemes, you do see like from iteration 2, like the model start to behave differently. So you can see some of the machine learning models can help you identify more optimal conditions more quickly. So like if you now like to see, okay, once you have this sampling strategy where they get applied, you can see this is a lovely video like currently in PNL, you can see like the robot starts to like make the synthesis and transfer the sample to the characterization station, and then the characterization steps are being taken. And we basically designed the sampling strategy to say which material, which conditions should be synthesized and tested. And here you can see like, some of the interfaces of how like the data has been collected. So with that, that's kind of like an example of like we first have the known workflow, and then we automated that, and then we started to design like a brain for like the automated platform. The next thing like I want to quickly share is like sometimes like if you have a workflow which is undefined, you can also like start to think about how you can use like the current like modular integration concept to build new workflows. So I call it an ARM designer. So like around like probably exactly the 1 year ago today, it's like our lab like in UW had like our first robotic platform is a liquid handling robot. It's open chance, and we call it Mara. The students were all very excited, and like they were like, oh, let's try to start to synthesize materials on the desktop. So we want to have a much compacted version of what our collaborators are having in PNL. So like we quickly start to realize, like in collaboration with Professor Dan Xiao, University of Washington, and she said, how about we try to synthesize some of the metal-organic frameworks, which is known like a family of materials with very versatile synthetic conditions. And with that, like she helped us to say, this is our manual workflow. We're going to mix the powders, we need to heat them, we need to like stir them with a series of the manual like steps. Okay, so that's fun. Like we quickly started to like develop the in parallel automated version where we believe our robot can take the steps. So you can see here, instead of making one sample at a time, we can have 96 wheel plates, and like our Mara robot can just work 24/7. Just like a little bit keep in mind that like demonstration is actually not a morph, it's actually food dye, so I can show different color to everyone. But that's actually really straightforward. But we quickly find like, well, making something can be fast because like you have a robot, but like, knowing what you actually made can be very challenging. So the challenge, like in a lot of the automated labs, are like how do you really design a characterization feedback loop? So in this case, ideally, we do want to have like X-ray diffraction patterns to tell us, did we make a new morph? Did we make the morph we want to make? What are like the common set product? So this is a kind of like X-ray diffraction pattern, but just like many other like high fidelity characterizations, we do not have this like machine in our lab. So that means this is low throughput, and like we cannot have like a very quick feedback to our machine learning algorithm. Very interestingly, like after making a few batches of the morph, we realized, well, actually, like if you take like a microscopy, optical microscopy of like the crystals we made, we realized, oh, actually the metal organic framework we want in this cobalt like based morphs, they look very different visually from like the common set product with the cobalt format. So that actually like solved our problem in terms of automation. Like we can just bring in like high throughput like microscopy, and this can directly scan over our like 96 well plates. So what does it mean is like by leveraging the computer vision techniques, which our group has been doing more and more over time, we started to like have the raw images instead of the high fidelity X-ray diffraction patterns, and that allows us to isolate the individual crystals, and we can start to calculate like based on each of the microscopic image we have, what are the impact of different synthetic conditions. So that allows us to redesign the experiment with a simpler characterization, and each of the image now becomes a data point that we can directly feed back to our machine learning algorithm to optimize it. So this is kind of like a demonstration of the phase diagram when we have like a synthesis done, and we directly take an optical image as the characterization. But the problem is not solved yet if we want to achieve a true autonomous workflow, because so far we know we can have a separate like optical measurements, like which is low fidelity but high throughput, but it's not part of our benchtop autonomous system. So then we actually start to bring in the new hardware. In this case, like one of our undergraduate designed like using like a CAD, like he drew it and designed like a module and printed it and put a high-speed camera inside, put a Raspberry Pi like inside, and so he can have like the through API control everything. So then that means like with this additional hardware module and also the software integration, now like our Mara autonomous platform can truly perform inline characterization. So if now, if we see like our autonomous system, we have like a single crystal girl system, which is benchtop size. And with that, like it has an autonomous workflow where you can automatically sample and then like take measurements, and then the measurements directly get fed into a Bayesian optimization, and that's direct to the next synthetic step. So this can happen within like a benchtop scale. So with that, that's really exciting. But like sometimes like you say, you have like some flexibility. You can like have a new module onto already existing like a liquid handling robot, and that means like as a computational scientist, if you say, Shijing, can you have your lab help me like to synthesize this new material? That means yeah, we'll try several like conditions. If it doesn't work, we can bring in new characterization, or we can bring in a replacement of the high fidelity characterizations to help us quickly scan a range of materials, a range of conditions. But after we built our Mara platform, a student one day came to me and saying, Shijing, you know what? I know you spent like 15K on that robot, and you told me that's the cheapest. I can just build it. I was like, oh, okay. And because we are in mechanical engineering department, and the students were very excited to just build autonomous system. I was like, okay, that sounds amazing. Let's do it. So I say, here you go. This is what you have. Can you start to build an autonomous system? And in this case, I said, Well, that's not limit us to liquid handling robot. What if like one day I want to make a new materials, I only have the structure. I don't know whether I will do liquid handling or I will do solid state synthesis. I want to try different things. Can we have a very adaptable, generalizable platform? So this is our project. I sent the student to get onto it. This is an example of a student working very hard on it. And gradually they start to put the base. They start to put the software, which actually controls the different arms. And they start to put together like the skeleton of the like kind of a robotic system. So like that's very exciting. And so my question would be like to the audience, how long do you think like from the first picture to the last picture, like it took a team of 2 like students?
50 days.
50 days. Yes, because last year I actually showed like it took us a month to put Mara together. So actually this is a summer project. The actual building was actually like I asked them to do it in 2 weeks. They say can do it 1 week, but in the end they actually put it very quickly together. That is after we already bought everything and they were just putting things together. You would say, oh, you know, is that because like your students are so good? They are amazing. But the true power here is we didn't invent this. This is the power of the open source hardware. So in fact, what we just built is an example system called Science Jubilee. And the Jubilee is an extendable machine for multi-tool fabrication. In the way, this is a framework actually developed by my colleague in human-centered design in University of Washington, Professor Nadia Peak, where like you can put multiple tools docking on this general platform. In fact, another colleague of mine, Professor Lilu Pozzo, she already adapted one of these scientific science jubilees for her projects, and she used it for sonication, which is a different purpose of what I was thinking in mind. But because this framework is so adaptable, you can do that. I think a lot of the audience here may be familiar with the concept of open source software. So here we just demonstrated with open source hardware, different labs can use a very well-documented document that allows us to replicate like autonomous system in a shorter time. So this is what the system kind of like look like as of now. Like it's still quite like empty because we are going to put a number of tools inside. But the idea here is that because it is very flexible, we can put a number of complex experimental workflows or new arms as we see needed based on the application, based on the materials, and also we can start to test different algorithms like through the API like freely. And I'm very excited for the future of the autonomous research with these more flexible systems. In the way it gives us a playground to try different type of algorithms and also workflows. With that, I'll conclude. So in my talk, I just showed like 3 examples of autonomous systems and all-in-one system where pretty much we have the human out of the loop. We designed the AI algorithm to just execute the experiment. We have the modular integration where like it's kind of like a joint like work. We design some of the modules to fit specific fidelity and data collection needs. We also have the open source hardware. In this case, like it's a very flexible, low hardware cost. So it cost around like less than $2,000 to put together for the last one. But of course, bear in mind with the high throughput all-in-one platforms, you also have the like benefits of being more robust because there are a lot of commercial options. If you are developing the autonomous system yourself, like often like you need to like figure it out like the reproducibility as well testing like different hardware options. But all of that, I just want to say we are in the era, we are redefining the role of scientist and human in the laboratory. We are no longer like just designing the experiment. We are designing like the workflows. We are designing the AI embodied robot. So which is a really exciting time. We are passionate about autonomous systems and I also want to make this talk a kind of core for collaboration. If you have like a theories you want our robots to test, if you have a chemistry system you want us to try to synthesize, I'm open to all the suggestions. With that, I want to thank my team, collaborators, and also happy to answer any questions.
One quick question while we switch computers again.
Yeah.
Yeah, very nice talk. So I understand the challenge of deviating pixel to grad center, but have you considered iTrad and around?
That's firstly, that's a very good question. It's like, so the example I show here is not specific for XRD. It's just an example where sometimes like when high fidelity data collection is what we need, is what's ideal, but with the domain expertise, you can replace it with a low fidelity, higher throughput characterization, which also do the job, and it's easier to keep it into the loop. Yeah, so I don't mean specifically for certain types, but X-ray is just an example. Thank you.